All right, welcome back. So let's continue our exploration of the available data types inside PostgreSQL. All right, and one thing that should be a given is that PostgreSQL comes equipped with data types that are meant to store text strings. There's actually a number of these inside the system. We have mainly used the text data type. So this last line data type here, this has been the primary use and will remain the primary use string representation that we are using in this course, because it allows for text strings that are of varying length. We don't have to decide for a maximum length beforehand, and text values grow as needed. That's very convenient and very efficiently handled in modern versions of PostgreSQL. So that would be the primary string representation that we are using in this course, that we'll also see used in modern applications. But there's more. There's actually a variant of that, a variant of such varying length strings that can have a maximum length of n characters. So if you know that your application will never will store strings that are never exceeding n characters, then that would be a suitable type, and it would also document in the type that there is an expected maximum length to the values. It might be useful. All right. We will see how this n is enforced and used during computation with these values. There's also a really a relic from the past, the char data type, char n, which can also store character strings up to a maximum length of n. Internally, such char n values are always stored with n character width. They are always printed and stored with n character width, regardless of their actual contents. We will come to this in a minute. So this lets the system work with fixed size character chunks of n characters internally, which can make things easier when it comes to the rearrangement or the pre-allocation of memory, but really has some strange behavior when it comes to applications. So you don't see char n used much in modern applications. But it's there, and we will spend a few minutes or just a minute with these. And then there's the variant without the n here. You see, this is just the char data type, which can store just one character. All right. So if we are talking about these n's here, these maximum lengths, then these length limits are actually measured in characters, not in bytes. For many character encodings, one character means 1 byte. There are modern character encodings, like Unicode, for example, where one character could occupy more than 1 bytes. And we've got functions in PostgreSQL that let us explore the actual length of characters of a string or the actual bytes, which might be even more of a string. All right. So the maximum string size in PostgreSQL, as you can see, is measured in bytes. It's a 1 gigabyte. All right. So if strings really get that large, they have to be special precautions are being taken to efficiently store such large strings. And internally, they are so-called toasted, which actually means that they are not stored together with the other values inside our tables, but are in some separate place where we can where we have enough space and the proper organization to store such large string values. But this is actually a topic for the DB2 course, I would say. So when we specify maximum string length in char n, varchar n, for example, then these length limits are indeed enforced. And if you try to store character strings inside these types that exceed the n regarding character length, you will receive a runtime error. So if you explicitly cast text to such types and you provide a length n parameter here, then the system makes sure to really truncate the string representations of your values to never exceed the length of n characters. All right. As I told you, it's the char n, the legacy data type char n, really has some strange behavior when it comes to its printing, storing, and also to its computation. So internally, it's really stored with a fixed width of n characters. That makes things simple and regular internally. They are also always printed with n characters. So even if we store a smaller string inside such a char n data type, it's always expanded to really occupy n characters, and it's also printed with n characters. If the string itself is shorter, it's padded to the right with blanks. So the symbol that you see here is actually a space symbol. So this is used to pad a shorter string so that they are reaching the length of n. Okay, so but these blanks, these training blanks, these padding blanks are removed before we do some computation before such character data types. So internally they are padded and they are printed with n with blanks to achieve a length of n characters. This gives you some regularity. Okay, but before computation happens, before we inspect the string, before we compare it, we will see that in a terminal in a minute. And then these padding blanks are removed because they have been introduced by a system in a way. So there's really some strange things going on. So you see char n values printed with a particular width inside your tables, but if you are then computing with these, they might be shorter because blank padding is being removed. All of this asks for confusion and chaos. So be aware that character n has this strange behavior. So let's see how this looks in the terminal. Okay, so this would be a string, a text literal with 5 characters. If I cast this to character 3, to char 3, then as the slide told you, some truncation is going on. So this will only hold 3 characters. The first 3 characters of this value will be preserved. Everything else will be truncated. So let's try that. Okay, there you go. 0, 1, 2 have been preserved, the characters, everything else has been truncated. You see the name of this particular table column here. It's BP char, and that's derived from the actual internal type name of this char3 data type. It's a BP, a blank padded character. So the BP reveals the strange blank padding behavior of the character and data type that I've just mentioned before. All right. So let's see how this padding actually occurs. So let's have some string values here that are actually fitting 10 characters or are even shorter than 10 characters. And we will take these 2 string values called TC after we've scanned them here from the literal table, these TC values, and we'll cast them into a character 10 value. All right, and as I told you, blank padding is going on, and this is what we will see in the output of this particular small query. Okay, so 2 values have been inserted in the resulting table, the 2 string values. This value has 10 characters and fits perfectly fine into a character 10 value. This guy has been extended to fit 10 values. It's been padded with 5 invisible space values here. So they are printed and stored indeed with 10 characters, but this leads to some strange behavior during computation with these values. Okay, so but this is the internal representation, padded with blanks. All right. I just wanted to remind you that for some character encodings, the character length is not the byte length of a string. Okay, so the database I'm currently working in is configured with Unicode text, and Unicode text characters may be encoded with more than 1 byte per character. And this is what we can see in this tiny example. You see, I brought the literal table again with me. And again, each of the rows only carries 1 string. This first row carries the string with character X. And in the Unicode encoding, the simple character X is encoded just like in the ASCII encoding, so with a single byte. Okay. When we look at the select clause, we will see that we just print the string. That's fine. We will print its length measured in characters, and for the X here I would expect a 1 here, And I will also output its internal length, the number of bytes, not characters, the number of bytes that have been used to represent that string internally. So, and the system function octet length can reveal that to us. So measured in characters using the normal length string function, measured in bytes using the octet length string function. Already for this particular symbol, this Unicode symbol, we will see that length in characters, just a single character, and the length in bytes will diverge. So this exclamation mark sign has this warning sign, has the internal Unicode code point 26A0. Internally in my UTF-8 encoded database, this already occupies 3 bytes. Okay, so octet length for this character, or for this warning sign, will be 3. And this string consists of 2 characters. It's actually the Unicode rendition of a woman of color. So it's the head of a woman with neutral skin color and then this darker skin color. If I have these adjacent, Unicode enabled system will combine these emojis to yield a woman of color. All right, so this needs 2 characters, but looking at the code points for these 2 emojis, we will see that a sum of 8 bytes actually needed to internally represent these 2 Unicode emojis. So let's see whether we can actually find that. All right, so you see the terminal embedded into my editor is already a bit overwhelmed by all the Unicode niceties, but the results are just what we expected. 2 single characters encoded as 1 or 3 bytes, 2 characters that are encoded internally using 8 bytes. So be aware that character strings might be encoded with more than 1 byte using particular encodings. So normally when we operate with textual values, when we compare them, when we order them and so on, when we concatenate them, when we slice substrings, then you would not need to care about the internal encoding, byte-wise encoding. But it's nice to know to really know what we are actually storing here. This might become relevant if we are storing millions of rows of stuff. And being aware of how many bytes the character strings that you are storing are occupying can be useful information. All right. So just to give you a glimpse of the strange behavior of the char data type, I've brought this sample query with me in which we apply the octet length and the length functions to values of type varchar and char 5 in this of length, maximum length 5 in this particular case. All right, so octet length applied to a char value will reveal the number of padding blanks that have been added to the value, if any have been added at all, so that we can really see the internal padding behavior of this char and data type. Let's evaluate that and then look whether the results make sense. So the octet length, so the number of bytes internally occupied by this string cast to a varchar 5 is indeed 5. All right, so truncation happens when we cast this textual value to a varchar 5, and yeah, these 5 characters are simple digits. They only internally use a single byte encoding, so 5 bytes are used to encode this prefix of 5 characters in the first line. All right, and you can see that we are really working with variable strings here, with variable length strings. Even if we cast this short string into a varchar 5, internally it will only occupy 3 bytes. So varchar n values are really of variable width. Okay, and they can adapt to width, just like the text value that we love and use so much in our examples. So really variable width adapting to the actual length of the stored string up to the maximum length of 5. All right. So it's different for char 5. So if we cast this value to a char 5, right, then internal padding will go on. Internal padding will go on, and this 3 character string will be padded to a 5 character string internally, and that's what we see here. indeed padding has been going on. All right. So, but be aware, when we start to compute with such a value, so this is the same value as in the row above. So a 3-character value cast to char 5, internally represented by a padded 5-character string. When we start to compute with such a value and, for example, apply the length function to it, then we see that all the padding blanks are being removed again, and we end up with just 3 characters. All right, so the internal storage format uses 5 characters, and this is how the value is printed. When we compute with the value, length is one such computation, then all the padding is being removed already. And you can see that padding indeed is removed. If we enforce such padding here with 2 padding bytes and then cast to char 5 and then perform computation, you will see that padding bytes are removed, and again we will end up with 3 characters for the field C5 that we've computed in this query. Okay, so I hope you're confused yet. So I can only raise my finger and warn you about the strange behavior of char 5. If this is really what you need, namely padded representation, storage, and output representation of these strings, then char n might be for you. Otherwise, I can only advise you to use the modern variant of that that is variable width, can adapt to sizes of arbitrary lengths, namely the text data type. Okay. Okay, so much for the different text data type available in PostgreSQL. All right. So let's switch over to their pals, the numeric types. So we have already seen int and float values, and I don't want to go deeper into these here. They behave just like the int and float values that you would know from your favorite programming language. But there's one particular additional numeric type in SQL systems, in database systems, and that's actually called numeric. Okay. So this is the very expressive and very nicely configurable numeric data type. You see that the full type specification of the numeric data type reads like this. So we are talking about numeric data types with this precision, and with precision, so this first parameter determines the number of decimal digits, that this particular numeric value will occupy. Okay, so the maximum number of digits that are available to represent values of this numeric data type. All right. Scale digits of these precision digits are being used as being used behind the comma. So that's the scale of that value. So this would be a precision 10 value with a scale of 3. So 3 of the digits are after the comma. Okay. You can see there are some abbreviations going on here. If I don't need the fractional part of that value, then I don't have any post comma digits with me, and this would be an abbreviation that is useful to have in such a particular case. There's also the abbreviated data type just numeric, which means that the precision of this data type is virtually unlimited. So in PostgreSQL, it's more than 100,000 digits. I think the accurate number is found in the editor if we switch over in a second. But this is really expressive, very wide data type that can extend to thousands of digits. And as you can imagine, there is no built-in machine support, no built-in arithmetic support in CPUs for values of such byte width, of such digit width. So arithmetic on these very wide numeric values has to be implemented in software by the database kernel itself. So computations, comparisons, arithmetic with such very wide numeric data types might turn out to be computationally rather heavy. So if you can do with integer data types, or maybe even the float data types, then maybe you should do that. if you really need very wide numeric data types, lots of digits, or if you need very exact arithmetics, so the software emulation of the arithmetic operations on the numerics does not suffer from the inaccuracies that your normal CPU would show if it operates with float or double values, then the numeric data type might be for you. It's truly a variable length data type. So the leading and trailing zeros are not stored. So trailing zeros in the fractional part here in the scale part are not stored. Leading zeros in the part before the comma in the integer part are not actually stored. These turn out to be really variable length data types. So very compactly and very efficiently stored inside PostgreSQL, but still computation might be heavy. So let's see how this looks in practice here. So you see this is arithmetic operation that I'm trying to perform. It will yield a ridiculously large result value. So it's 2 to the power of 100,000. This will yield a really large value. You see my explicit cast here to assure the system that I'm really intending to perform numeric arithmetics here, numeric without any precision or scale that has been selected. So use as many digits as you can, PostgreSQL. And you see these are the actual system limits that are currently enforced by the implementation of PostgreSQL. So lots of digits after and before the comma or the decimal point. All right. Okay. So let's see what comes out of this. I'm switching timing on and off here. Let's see. So this took some time to compute, but the value really is ridiculously large. Let me scroll upwards. I'm scrolling. I'm still scrolling somewhere. This is the very wide display. This is the very wide display of the numeric value that has just been computed. Okay, so there's actually no practical limits to the computations of numeric values of this particular kind. Okay, but we pay a price. We pay a price for the software implemented arithmetics on such very wide values. And to make that point, let's look at this sample query here. You see that this is a query, this is the main query, and this query is scanning a table of 1 million rows. These rows are called T, and they have just one field, the field X, in which we will find a numeric value. So what we do here is arithmetic on these numeric values. Tx plus Tx is a simple arithmetic expression. If Tx is indeed of type numeric, as it will be in our example, then this plus operation has to be implemented in software, and it will take its time. So we get hold of such a 1 million rows table just in the CTE in this with statement above, where you can see that I'm just filling the 1 million rows with numeric values which will fit 8 digits before the decimal point and no fractional part. Okay, the explain analyze on top here will measure the actual evaluation time that we need to perform this particular query. All right, we will see the plan, which is not of that interesting in this case. It will be very simple, but we will see how much time is invested to perform these 1 million arithmetic operations for us. So let's evaluate that. Going on, taking its time. All right, and then there we go. It's 4.6 seconds. Will probably be faster on your system that's not loaded with video encoding, but it takes its time. 1 million additions here take 4.6 seconds. I can repeat the same example using the integer data type. The integer data type of just 4 bytes, because 4 bytes of integers will suit the range of values that we are operating with from 0 to 1 million here. Okay, so the same query, but the type has changed. We are operating over integers, and we expect this plus operation to be performed more efficiently. to be even supported by the arithmetic instructions of the CPU that is built inside your machine. All right, so let's repeat that. All right, so that's about double the speed of arithmetic operations here, and you can expect actually significantly larger differences once you end up with queries that perform more than just simple operations like additions on your numeric data types. Try to find a numeric data type that suits your needs and is not over configured like the numeric data type that we are using here. Okay, because such numeric data types can be really of almost arbitrary width, we can of course encode lots of information inside one such single numeric value. That might sound strange. So what would you encode besides the numeric value itself? But just to give you an impression of the amount of information that is actually stored in such a very, very wide numeric value, I brought with me an example of computation over such numerics that is quite interesting. It's called Tapas formula. And Tapas formula is just the evaluation of a simple arithmetic expression, one that you can see here. And as you can see, this arithmetic expression has two parameters, namely the x here and the y here. All right. And whenever this arithmetic expression yields a value larger than 1/2, then we would plot a pixel at coordinates x and y in a small rectangular picture. All right. So you give me x and y values. I will evaluate the arithmetic expression. If its value is larger than 1/2, then that means plot a pixel at coordinates x, y. Otherwise, plot no pixel. And you can see what happens here. You can see the plotted pixel picture below here, and it appears that this formula has been able to plot itself. Really think about it for a few seconds, and it's really mind-boggling. So this is a particular formula. I insert x and y values here, and what I end up with is the pixelated rendition of the formula itself, as you can see. The magic that happens here is that the x and y values that I'm considering are not arbitrary. These values regarding x range from 0 to 107. This is actually the pixel width of this particular picture. But the y value is ranging from k to k plus 17. So this is actually the 17 that you see here. This is actually the height of this pixelated picture. But the k value itself, and that's highlighted here, is one very, very, very wide numeric value. It has more than 530 digits, as you can see. Lots of information can be encoded in that many decimal digits. And Tapas formula extracts these bits of information that are encoded in this super wide numeric value and uses this to perform a nice and cheeky rendering of the formula itself, of Tapas formula. So let's play with this. Let's switch over to the editor and to a file Tapas formula that I brought with me. And as you can see, this file contains this super large numeric value k. This is the super large numeric value k. All right, let's scroll to the very end. There it is. So that's the super large numeric value k. More than 500 digits. Okay. So what we will do now is just evaluate Tapas formula. Evaluate Tapas formula for different x and y values. And as the slide told us, we will let x range from 0 to 106 excluding, so from 0 to 105 including. And y will range from k to k plus 16. All right. All right. So these are the the coordinates, the x and y coordinates that I will insert into this formula. This is just the SQL variant of the formula that we have just seen on the slide before. Okay. All right. So as you can see, this will yield a Boolean value. This is the value of this field will be the comparison with 0.5 with 1/2, and this will just a Boolean value. A true value will mean the pixel is set. A false value will mean the pixel is not set. So all we can see here is just the evaluation of the arithmetic formula for different x and y values. Okay, what we get here is a CTE, a temporary table that encodes the picture. So at x and y coordinates, we will find a Boolean value that will tell us whether the pixel is to be set, yes or no. And then we use some very simple string aggregation down here to just turn these Boolean values into a nice two-dimensional picture, as you can see. All right, so we will just scan over the rows of our encoded picture. We will group by row, so by y coordinate, and inside one row, we will aggregate a string ordered by the x coordinates, so from left to right. Okay, so for every row, in each row going from left to right, we will inspect the pixel that we find there. And if the pixel is true or set, then we will output this block. Otherwise, we will output a blank space, which is the white pixel or the non-set pixel in a sense. Okay, and everything that we find here will be aggregate inside a row, will be aggregate into one row string. All right, and we will emit these row strings in proper row order so that we can turn this pixelated information with XY coordinates into a nice two-dimensional string rendition using just this single group by with a string aggregate query. This is actually an idiom, a trick of converting such XY encoded pixelated data into something that we can actually look at that we'll find sometimes in this course. So now and then you will find this trick applied. Okay, so let's evaluate that. Let me first reduce the font size here so that our rendition of Tapas formula will actually fit. So let's see what's inside this very wide numeric value k. And go. Oh, there you go. It's not the Tapas formula, it's something else here. All right, so whatever we have encoded in pixelated form inside such a numeric value can actually be recovered by Tapas formula and then printed in two-dimensional form here using pixel blocks and spaces. Okay, so what we find here is advanced SQL. Okay, so all of these bits, these bits of the 17 times 106 pixel wide picture are actually encoded inside this very wide numeric value k. All right, you can play with these values k. You can generate new values k. I can show you in the forums how you can generate new values k. So I brought the advanced SQL encoding with me. There's also the original Tapas value encoded inside the system. I think it should be this. This is Tapas formula in its original form. This can also be rendered. All of these bits are stored in such a numeric value. Plenty of space to encode information. But probably an abuse of storing information inside such a numeric value. We will find better ways to store lots of information in relational database systems. All right. So, so much for the textual and the numeric data types in PostgreSQL. So, if you stay tuned and keep listening for and watching for the further videos, we will expand the family of data types that we can store in table cells in a SQL database systems. See you then. Bye.